So let's see, continue. P3, a little review, just to make sure. This is as ugly as I can make. So 4 minus 2 squared roots of 3 over 5 squared roots of 6 plus 1. Now the trick here is you cannot leave an irrational number in the denominator, a radical in the denominator. So I need to multiply top and bottom by? No.
It's not by.
What's called conjugate. Conjugate. And the conjugate of 5 squared roots of 6 plus 1 is? 5 squared roots of 6 minus 1. So we're going to multiply top and bottom by this piece. And expand it all out. Now this one's horrible because you have to expand the top and the bottom. Usually it's just one number on the top and I just have to distribute it. This one you have to FOIL both of them. The problem that people have with this is they'll conjugate the bottom and get the answer right there, but they'll do the same process to the top, leave the middle term off, and get the answer completely, crazy. So make sure you FOIL both of these out or distribute both of them out. 4 times 5 squared roots of 6. 20 square roots of 6. 4 times negative 1 is going to be negative 4. Negative 2 square roots of 3 times 5 square roots of 6. Negative 10 square roots of 18. And negative 2 square roots of 3 times negative 1. Positive 2 square roots of 3. Try to get that word positive or negative in there because those become your operations. All right, all over. And I'm going to expand the entire bottom out again. 5 square roots of 6 times 5 square roots of 6. 25 times 6. The 6 just pops out of the radical. So I'm giving it 2 factors. The outer and the inner, one's going to be positive, the other one's going to be negative. They're going to cancel. And then positive 1 times negative 1 is negative 1. Okay. And then just simplify the top as much as you can. Can't do anything with square root of 6, but square root of 18. Well, that's 2 and 9, and 9 is 3 and 3. So I can pull out a 3 and leave behind a 2. So this becomes 20 square roots of 6 minus 4 minus 30. That 3 is going to come out and run into the 10. You get 30 square roots of 2 is left behind, plus 2 square roots of 3. All over, 25 times 6 is 150, 6 quarters, minus 1. 149. That's horrible. I don't think anything goes into all those numbers, so we're pretty safe. So that was just the last thing that we dealt with last class. All right. The end of P3. It's nothing hard, it's just something that people hate dealing with. Whenever you see the word rational, what comes to mind? Fractions. And when you're dealing with fractions, you have to be really careful when the difference between multiplying, dividing, adding and subtracting. Adding and subtracting requires common denominator. And multiplying requires just, straight across. All right, so what does it mean to be a rational exponent? For instance, if I say 4 raised to the 1/2 power, what does it mean? And that's what we have to kind of delve into. So I'm going to start kind of backwards. If I start off with the square root of 4, what's that equal to? I hope so, 2. It's positive 2 because of, what's that called? It's a word. It begins with P. Something root. Principal root. Principal roots of even indexes always have to be positive. Okay. We'll come back to haunt us later. I can write 4 as 2 squared. That's legal, right? Because 2 squared really is equal to 4. So my question to you is, if I have 2 squared, and I raise it to some power, I want it to equal to the first power. What power do I have to raise it to get that power of 2 down to 1? 1/2. So if I multiply by a power of 1/2, remember, power to a power you're going to multiply, 2 times 1/2 is 1. What kind of numbers are 2 and 1/2 when you multiply? What property is that? What is it? Inverse. It's inverse because you're coming up with the identity of 1. So 2 times 1/2, those are multiplicative inverses. It gives you 1. So I can write 4 raised to the 1/2 power. I can say that's equal to 2. 4 raised to the 1/2 power is equal to 2. All right. Similarly, if I have the cube root of 27, well, what's the cube root of 27 equal to? 30. But 27 I can write as 3 raised to the 3rd power. 3 raised to the 3rd power. So same argument. If I have 3 raised to the 3rd power, what power do I raise it to get back to my answer of 3 to the 1st power? 1/3. The multiplicative inverse of 3 is 1/3. Okay. So that means I can take 27, raise it to the 1/3 power, and my answer is going to be 3. Sounds reasonable, right?
So essentially what you're getting is 27 raised to the 1/3 power is the same thing as writing
The cube
27
root.
cubed.
Cube root of 27. Cube root of 27, correct. So here's my last little question on this. If I have 81 raised to the 1/4 power, what's it equal to?
1 cubed, 4th root
It's the 4th root of 81.
of 9.
No, it's not 9. That's the square root of 81. 3.
Ah.
Because it's 3 times 3 times 3 times 3. 4 threes. If I have 32 raised to the 1/5 power, trust me, there's only one answer to this one. 2.
405 on that.
Well, it's 2 because this is 2 and 16, 2 and 4, 2 and 2. I messed up someplace.
It's 2 and 8.
Ah. 2 and 4, and 2 and 2. And then there's 5 2s, so it pops out as a 2. Because it's the 5th root of 32. It's the exact same thing. All right, so that's what rational exponents are. They're just kind of explaining what's going on with the number. So what happens if I do this? 27 raised to the 2/3 power. Now it's not a 1/3 anymore. I have this 2 introduced. But there's a way of getting 1/3 to equal 2/3. What do I have to multiply it by?
You said what?
What times 1/3 will give me 2/3?
2.
2. So what we can do with 2/3 is we can separate it into the 1/3 part and the 2 part. Break it apart just a little bit, and there's a reason I need to do that. If I do that, I can rewrite this as 27 raised to the 1/3 raised to the 2nd. Because a power to a power, you just multiply. So here I have 2 times 1/3, which gives me 2/3. I can go backwards. So these things must be equal. Well, what's 27 raised to the 1/3 power? It's over there. 3. So this becomes 3 squared, but 3 squared is 9.
So that's the same thing as the cube root of 729.
Squared.
Yeah, squared.
Squared. So the bottom number becomes the index. The top number becomes its power. Its regular old index or integer power. All right, how about this one? Trying to think of a good one. 16 raised to the negative 3/4. 16 raised to the negative 3/4. Now, the bottom number becomes the index of the radical, so I highly suggest you take care of that first. So this becomes a root. What root? All right, this is the 4th root of 16, and you're going to raise it to a power. What power is it raised to? Negative 3. This way, if you do it in this order, you can switch the order on these powers. 1/3 and 2 here can flip around because of the commutative property. of multiplication. But I highly suggest you do the root first and the power second, because the root will make the number smaller, the power will make the number bigger. So if you do it in that order, things don't get out of control. All right, what's the fourth root of 16? 2. But it's being raised to the negative 3 power.
So you flip it.
And it becomes
1
1 over 2,
to the third.
2 to the third. So this is 1 over 2 to the third, better known as 1/8. So 16 to the negative 3/4 power is the same thing as 1/8.
That's a lot of breaking down.
But that's all math is.
I know.
Pieces, lots of little pieces. Where's my eraser? There it is. All right. So that's what it means to be a rational exponent. Let me write it in definition terms, so it always works. In definition terms, it works out this way. A raised to the p over q is the same thing as the q root of a raised to the p. Or it could also be the q root of a raised to the p. The p's location could either be on the far outside or it could be on the inside. And that's that commutative property of multiplication. It allows you to switch places. So how about this? For example, a little simplification problem. Negative 8, x to the 9th, y to the negative 12th, raised to the 2/3 power. Well, after this, I'll have a little cautionary. All right. What's negative 8 raised to the 2/3 power? It's the cube root of 8. Oh, I'm sorry, cube root of negative 8, which is negative 2. But then you have to take negative 2 and square it. So you do the cube root first, and then you do the square on it. So negative 2 squared is 4. So it's a cube root of 8, cube root of negative 8, which is negative 2, and then negative 2, and you're going to square it, gives you 4. All right, what happens when you have x to the 9th raised to the 2/3 power? Power to a power, you multiply. What's 9 times 2/3? In other words, what's 9 times 2/3? 9 times 2/3.
6.
It's going to give you 6, because 3 goes into 9 3 times, and 3 times 2 is 6. I'm waiting for someone to say 8. X to the 6th power. All right, y to the negative 12th raised to the 2/3 power. Ooh, not yet. Don't do it yet. Here I'm just working with the power. So let's see. Negative 12 times
Oh, it's a negative 8.
2/3. So 3 goes into that 4. 4 times 2 is negative 8. So you get y to the negative 8. Could I have brought the y to the 12th down first? Yeah, that's what I usually do. I'm just doing what most people do. Either way works perfectly fine. What do I do with the y to the negative 8? So you get 4x to the 6 over y to the 8. Yay! That's not that bad. So when does this get bad? See, fractions under multiplication are nice. They usually behave nice. And if they don't, it just means you have to multiply and keep a fraction. The ones that I worry about are things like this. When there's fractional exponents, but they're not being raised to some other power, so we can simplify it nice. Yeah. 8 over 12? 2 over 3. 4 goes into both of them. But when you get to x to the 2/3 divided by x to the 3/2, what do I have to do to the powers? So let's see, 2/3 minus 3/2. How do you subtract fractions? Without a calculator? Common denominator. What's the common denominator between 3 and 2?
6.
So I'd have to multiply top and bottom here by 2, because 2 times 3 is 6. And over here I'd multiply top and bottom by 3. And we now have a common denominator of 6. So here's a weird question that most people don't know. When you write this fraction, it's going to have a 6 in the bottom. A single 6. Why?
Because it's,
A common denominator, but what property? Think about it. It is the distributive property. Anytime you have two x's and you add those like terms together, you end up with a single x. So what happens here is you have a common denominator of 6, and you're actually factoring out 1 6, adding the two numbers in the top, and then bringing the 6 back into the denominator. So when you add fractions with common denominators, you're actually using the distributive property. No one ever taught you that, I bet. I always wondered why the number stayed the same. I mean, you had those elementary, here's 1/3, here's 1/4, I need the same number pieces of pie in each of them to make them equal size. That's an elementary explanation of why you need a common denominator. This is the real reason. So here we have 4 minus 9, better known as -5. So this is x to the -5, 6. Okay. What about y to the -1/2 over y to the 5, 6? What do I do with those powers? Subtract them, so you get -1/2 minus 5, 6. Common denominator? 6 again. So I have to multiply top and bottom here by 3. The common denominator now is 6. In the top you get -3 minus 5. And -3 minus 5 is? So you get -8, 6, but if you put that on a piece of paper, I get mad. What do you do with -8, 6? Reduce it, it's -4/3. I've had people on a test leave 5/10. Seriously, 5/10. 1/2. All right, so this becomes y to the -4/3. So rational exponents just take a little bit of extra time to get those common denominators sometimes, but don't use them all the time. It's only when you add and subtract. Am I done with this problem? No, they both have to go to the bottom. So it's 2 over 3x to the 5, 6, y to the 4/3.